Right, so welcome back. We're going to have a bit of interlude away from our kind of business enterprise type program, and we're going to talk about something very fun. I did a little bit of work on the demo with Andy, so if it breaks, it's probably my fault because my unit tests are all flawed. Andy needs no introduction, obviously, so I'll just let him carry on and talk about small devices and Windows Azure.
Okay, great. Well, hello everybody, and I'm sorry in advance for being a little bit technical. The day so far has been very enjoyable, and it's been no code. So I'm going to rectify that by doing a lot of code. Maybe I can get a show of hands. Who here is familiar with C#? Great, and you can all code in it, and you can understand when it's just loads of code on the screen. Perfect. Okay, so I'm going to talk about devices and Windows Azure, but in a slightly different way to what a lot of people regard as devices. So not just mobile phones, other stuff. And let's get on to it. Who am I? I'm Andy Cross. Hello. And I am founder of the UK Windows Azure user group, so it's my pleasure to be here at one of our events and do a talk. And this is what we're going to have to get through before you can have another coffee, so bear with me. We're going to go over what I mean by devices, the scenario, and what an embedded device is, and then what Windows Azure brings to the table. So devices are literally everywhere. There's been an unprecedented growth in the number of devices. Already, right now, there are 9 billion devices in the world, and that's network-connected devices. That's everything from sensors to things embedded in phones to all kinds of real-world devices gathering data at all times and communicating over the internet in order to be part of this amazing thing called the Internet of Things. So if there are 9 billion devices predicted to go up to 24 billion by 2020, there is something around here that needs to be connecting everything. If we imagine that we have a very scalable back-end that is connected by all these devices, and I did a little bit of research in this, and Node.js is regarded as incredibly scalable and incredibly lightweight, so it's very good at handling these sort of requests. If we had a Node.js server that was taking 1 kilobyte of data from these devices, these 9 billion devices, it works out that you need 100,000 servers in place to be able to stay online, to be able to cope with all of these messages. And that's only if you take a single request from all these every hour. If you're doing something much more complex than that, or you're building a more heavy system, maybe you're trying to control fridges and you want to capture a lot more information around what that device is doing, maybe 1 kilobyte every hour isn't very much, and you're going to do a lot more than that. So we end up with a scalability challenge, and that's where Windows Azure comes in. So in terms of workloads, I like to talk about workloads quite a lot. Really, what we're talking about here is why the cloud is suited to specific things, about whether the device is reporting periodically. Maybe that would be an on or off type of workload, a type of workload where you might want to turn off your servers when you're not expecting any kind of traffic from your devices. Maybe you've got a new market release and you're trying to sell lots and lots of devices and you're expecting your capacity to have to increase rapidly. That would be a growing fast type of workload. And maybe you have bursts in your... maybe you have bursts inside your devices. Maybe they report on errors or report on activity that happens in the real world. So perhaps you have predictable or unpredictable bursts. Again, the cloud is suited to these types of workloads. So, a scalability challenge. Let's have a look at what we mean by this. Your devices are traditionally broken down into a number of categories. Desktop devices can be connected via the Internet of Things to be reporting on what you're doing on your machine. Maybe it's gathering productivity information about what you're doing, sending it across to remote services, so you can see how many lines of code you wrote in a day or something like this. Mobile phones can be connected to these same sort of devices, background processes, push notifications, all this kind of device interactivity. And embedded systems. Now, I've listed a limited number here, Nike Plus. I don't know if anyone remembered this. It was something which fit into your trainer and would communicate via a mobile phone into the internet. But what it was using that mobile phone just as a bridge onto the internet. The device itself was gathering all this information about where you've been running, and then it would communicate over the internet to a Nike server, and it would then like to see your exercise logs over n length of time. Now, this is was very, very successful, and it's actually a pattern which has been adopted by a lot of other people. A lot of other companies have released products which go over a network hop to some kind of back-end system that allow you to trace your activity over time. So a really key point I want to get across is this device digital exhaust, which is basically all the stuff coming out of devices. Devices are incredibly chatty things. If it's sensor information, it's being gathered all the time. It's a constant workload, and devices can be much, much more chatty than people. So in terms of the number of packets of data sent out by an individual device compared to someone sat at the laptop, you can get much, much more network traffic and therefore compute workload you need to do with the remote side from devices. And especially when you consider that devices can be in your shoes and on your clothes and all around you. So there can be a huge amount of digital exhaust at all times. And especially as time goes on, things get smaller, things get cheaper, things get more actually possible. And so, the capacity to do this only really is feasible with a cloud estate. So before we go into anything slightly more codey, traditional devices, we know what these are. These are computers, these are laptops, these are ultrabooks and even to a degree tablets, although that's maybe below in the lines. And they have all kinds of fully featured clients from all these presentation languages, but more importantly, things that can communicate up to a remote server. So like the Windows Azure SDK for table storage and the storage client, right? It's available for these full devices, and you just plug it in, you drop it in, you consume it, it goes, it's fine. So that's very interesting, and the same thing applies on mobile devices. It's, again, drag and drop a library that somebody else has already done for you, and it will just work and send your data up to the cloud, and away you go. Fantastic. But where there's the real challenge on embedded systems is that on a limited processor with limited memory and a very small amount of security cryptography possible on these devices, and there are no SDKs available, so you have to write your own. Now, I find this a really interesting part of Windows Azure, that you can do this, that it is not a walled garden, that all of the standards are open and published. So you've got a microprocessor, you've got a chip and a network connectivity and nothing else. And you can still use all of these remote services because you understand that it's a published schema, a published service interface that you can just communicate with. And because you can do that, and it's an open platform, you can then take this small form factor, which is what embedded system is really about, with limited resources, and you can turbocharge it. You can say, I know I can only store 5 kilobytes on my flash memory because there isn't much of it, but if I send a network packet off to Windows Azure, I can have 100,000 servers sat there, all of which are just sat there waiting to do work for my little device. So my little device doesn't need to be that capable if it can communicate to something which is more capable. So it's a very interesting aspect where you can remove these resource constraints and actually make these small things capable of a lot more. Okay, so you can, with Windows Azure, provision huge amounts of compute, and maybe you can consume that through something like a HPC interface, which will do things like distributing workload and giving you the results back. You can have hundreds of terabytes, as we were hearing this morning, of data storage in Windows Azure. So if you have a camera, for example, you could have a camera which is constantly taking photos and streaming them up to Windows Azure, never worrying about filling up its SD card. You can have everything geolocatable. So devices are very portable. These embedded devices, you can pick them up and go with them. It might be in your shoe at all times. Now, that, if it's going to connect over the internet, is going to have a big problem if all of your servers are sat in Europe and you're on holiday somewhere in America because of the latency involved. But with the cloud and the geolocatability of the cloud, you could have a data center very close to you servicing your embedded devices at all times. And there are interesting infrastructure services that you can get a very quick leg up, such as mobile services and media services. We've got some talks around some of these tomorrow. Mobile services in particular is very interesting for this because it's a very rapid application development and a very lightweight interface all over a REST interface. So it makes it very simple for these devices to communicate with it, although actually targeted at mobile devices rather than embedded devices. And I'm going to do a few demos, which we'll get to in a few moments. What these demos do is actually decrease in complexity. So the first one is very complex and there's lots and lots of stuff. The second one is a lot simpler and just does one thing. And the last one is incredibly simple and doesn't really do anything. But that means once we get over the first hurdle, everything else is nice and easy. So back to the point. There is no Windows Azure client for embedded devices. There is no... Well, because what is an embedded device? It's such a broad definition. Are you talking about microprocessor chips? Are you talking about a single type of that written in C, or are you talking about something which is assembly only? So what is this device? How could you write a client library for it? You couldn't. So because it's an open standard, you can write your own, and this is, getting on to my talk, the main part of my talk, it's a demonstration of the openness of this cloud platform. So what device are we talking about today? We're talking about something called a Netduino, which, is anyone familiar with a Netduino? A few people. Oh, wow, that's great. They released a new one yesterday, Netduino Plus version 2, which has got loads more memory than the one I'm using, and if I had that, and it hadn't released it literally just yesterday, everything would have been so much easier. But let's go into what the Netduino Plus that I do have, version 1, is capable of doing. So start off with the .NET MicroFramework, or NetMF to its friends. It started out in around 2005. There was a demonstration by Microsoft with this SPOT team. SPOT is Smart Personal Objects Technology. It rolls off the tongue, isn't it? And it was a watch which communicated with these SPOT services, which were Windows Live, and it would send messages over, I think it was the public FM radio bandwidths, and they would pick them up, and you would have all this live information about news and sports came on this live services, and it would appear on your watch. So your watch, it was a bit of a large watch actually, but cool in a retro. It's not as big as a laptop, but in a cool sort of retro way. It had a touch screen on there, and they would have the live news on there along with the time. And the time actually being quite a difficult one, as I'll demonstrate later. And this device was made by Microsoft. And what was really interesting about it was that they didn't code it in C++ and then compile it onto the assembly. They didn't do it low level. What they did was they made this entire framework, and they took the .NET framework and thought, well, can we get that to run on a really small device so that every existing .NET developer out there can suddenly start doing embedded programming? And that's what they did. They created Spot, which they eventually renamed to the .NET MicroFramework, and then they open sourced it in 2009. So you can go on netmf.coplex.com, and that is literally the framework. You can go in there and explore the class library and download your own and do whatever you like with it and see how it works. So it's an open source .NET framework. And they launched in 2010 a netmf.com community site. So you can go on there and get loads of information and case studies. But really, what is it? It is .NET running on a chip. There's no operating system, so it's not like the normal .NET, which runs on Windows, or if you're on Mono, runs on some indeterminate operating system. And It's running directly on the chip. You can do all kinds of interesting stuff with it. You don't necessarily have to have a memory management unit, so you can have very resource-constrained devices. Providing you've got 64K of RAM on your device, you can run the .NET MicroFramework on it. And I was thinking about this the other day, and I think that kind of means that some of the early Spectrums you'd be able to run the .NET MicroFramework on if you could just compile it to whatever crazy chip it's got. But yeah, and you can run, I don't know why you would, but if you wanted to, you could run VB as well, because it now supports VB on the chip in exactly the same way. Only the last version, which is 4.2, allowed that. Or was it 4.1? Anyway, so a very recent version allows you to do VB if you happen to be insane. But what else is brilliant about this? Hello? No, this only works on microprocessors on chips. So the question was, does it run on Linux as well? This MicroFramework, and the answer is that no. If you try to compile it down to that level, you'd be sort of compiling it to run on your Intel CPU. So it wouldn't be compatible with that unless you had a porting kit. So there's like tiers of what you do to compile a firmware for the .NET MicroFramework. You take the .NET MicroFramework sources, you build something called a porting kit, and you take a porting kit implementation. You take the porting kit generic version Microsoft provide, and you write in C++, lovely enough, a implementation specific to your chip that means that the high-level framework classes know how to communicate to the low-level device-specific things. But the person that does that is the person who sold you that chip. So you buy a Netduino, and the guys at Netduino, Secret Labs, have already taken the sources, made a specific implementation that works on the device, on the chip in the device, compiled it, and shipped it as a ready-made firmware. So as a consumer, I pick up this firmware, and I put it on the chip. Well, it already comes pre-compiled with one, but say you wanted to upgrade the version or something, you put the firmware back on the chip, and then once you've done that, you're just consuming the high-level classes, things like ints and strings and web requests, as we'll get to later. So no, it doesn't work on Linux, but that's because it's at a super low level where there is no operating system in the equation, and it's designed for devices where you can never put an operating system because there's not enough memory space and capacity. Okay? Andy?
What version of the framework is it most like?
Good question. And when is the framework complete, and why are the bits obviously missing, like string.parse and string.replace, which makes everything a complete nightmare. It is most like probably version 2. It's got variable languages, but it's not dynamic. So it's not the DLR stuff. It's more like what the CLR was before it became a DLR. You can do generic types, but anything which is more than that, anything which is more dynamic isn't supported. For example, the dynamic keyword. And I'll get onto this in a second, but the device vendors, I said there's this idea of a porting kit, that the device vendor will take the high-level .NET classes and make this sort of intermediary layer that makes it work on that particular chip. They don't necessarily just do that. Some of the time, they'll go, my device is actually on the sort of small side of capacity and resource capacity of these devices. So I won't compile in the support for cryptography at all. So it makes the framework much smaller, and that means that when you're using it, you're still using the .NET framework, but if you try and call something like system.cryptography, what am I doing? SHA hash or something, it will say not supported. It'll throw a not supported exception at you, even though it's in the framework, and you would expect that it would work. On one device it would work, on another it wouldn't. So there are sort of limitations around here. So am I okay to carry on? Okay. One last point about why it's so awesome, apart from that it runs on freaking chips, is that you have full debugging support, and you write code for it in Visual Studio 2010, because it's not an upgraded version for 2012 yet, but it's Visual Studio. So that's amazing. You can step through, put breakpoints in. You can use the immediate window and the output window to see what's going on. It's not like classic embedded development. If anyone here has had any experience with classic development, writing in low-level C and putting onto a chip, you don't get any of that. You don't get any of those tools. If something goes wrong, you have no idea what it is. You're going to have to like try and find the logs somehow. Did you even make any logs? Could I even create logs? Because I didn't have any device capacity to do that. And when I run out of memory, well, I've run out of memory. How do I even report that I've run out of memory? Because I'm on a chip. So it's impossible. But with this, .NET running on a chip, you plug it in via a USB cable directly into Visual Studio, and you can step through line at a time. What's it doing? What's it doing? What's it doing? And I'll demonstrate this later, and I think that's just absolutely freaking awesome. Twice I've said freaking in a sentence. Anyway, so very close to what Andy was saying, comparing it to other frameworks. So there are quite a lot of .NET frameworks these days. I don't know if anyone noticed. There's the .NET framework. There's the .NET framework client library, which was in 3 and 4. And no one used it, as far as I know. The only experience I've ever had with it was that nothing would work when it was supported in the client. So everyone goes into properties and goes, oh, it's not. That's why it's not working. It's the client thing. I'll put it back onto the full version. And that's the only purpose of the client framework, as far as I can see. Yeah, okay. Then there's the .NET Compact framework, which is most of the full framework cut down a little bit to work on small devices like Windows CE, which is an operating system or something. And then there's the .NET Micro framework, which I think is better. But they are horses for courses. They have their own strengths and weaknesses. If you've got loads and loads and loads of RAM and loads of CPU, you should use the full .NET framework. If you're on a resource-constrained device, you use the Micro framework. If you have a really well-compiling application and you want it to break, you should use the client framework. So today's devices, haha, excellent. It is a Netduino Plus by Secret Labs. And I mentioned before that a version 2 came out yesterday. That means that all of these stats are sort of old now. So it's 48 megahertz, which is actually pretty quick, an ARM7 processor. The new version is it's like 6 times faster. And if I could do maths, I'd tell you what that was. It also has 300 and something, or I think it was this morning, I literally cannot remember what they are, 600 and something code storage kilobytes, and RAM, again, which is like 6 times higher. So the new devices are massively more capable, but still, if you compare that to a mobile phone these days, it's not actually got much capacity on it at all, and it's still got this very limited form factor. And this is the really important bit. If I can just kind of go over here. The bit that you're actually doing anything with is that bit there. Just the actual CPU, as it were, the processor, integrated chip on there. Everything else around here is for humans. So this is a button. This is it's an Ethernet integrated chip. That's the Ethernet port. There's a micro SD slot in here. These allow you to communicate to external devices by plugging in basically wires. This is a power jack, and there's a micro USB jack. And a lot of this stuff, basically, you wouldn't have in a production system. You wouldn't design it to be this large. You would have something which was just the size of this chip here, literally the size of your thumbnail. Now, if you want to do an off-the-shelf product and you don't want to do a custom design of a board, you can get something called a Netduino Mini, which is a lot smaller. It's still bigger than you could do if you do a custom design, but it's a lot smaller. And it doesn't come with things like the Ethernet jack, and it doesn't come with a power supply jack on there, so you have to do that yourself. But of course, that's part of the fun, really. And why is it called a Netduino? Well, it's a .NET MicroFramework version of an Arduino. And Arduino is an Italian company who make an open source hardware for hobbyists and increasingly actually for people in commercial applications. So it's the Netduino guys have taken the open source hardware, which is actually something it was new to me when I first heard it. Well, I think everything is the first time you hear something. Anyway, they've taken the plans for this open source hardware and they've changed the chip to something which is capable of running the .NET MicroFramework, and they've kept the form factor the same. So that means that any adapters that you get which are built to go on top of the Arduino, and these things are called shields. So you get a device like a Wi-Fi shield, which just does the integrated chips for Wi-Fi's. And you can just sort of plug it on top of the Arduino, and these blue bits that you can see in the diagram, well, photo, they're actually lined up automatically. So it slots in, and it'll just then communicate. If you write your program, you can use it. The same thing will work on the Netduino. You can just put the same shield on the top and then write in C# to integrate with the Wi-Fi shield or whatever it is you want to do. Okay, so I promised you some code. I'll be kind. And I'm going to do a 120-second tour of .NET MicroFramework, and then I'm going to go into things which take a lot longer than 20 seconds. So you write in C# or you write in Visual Basic, if you're a lunatic. You use Visual Studio, and you can use Visual Studio Express. By the way, I'm very sorry if anyone here likes Visual Basic. I'm sorry for you, I mean. So you can use Visual Studio Express Edition. That will work. So you can get going for free. You can debug and deploy via USB or by serial if you have a serial connector. Debugging works amazing. You can actually go and step through your code, which we'll do in a few minutes. It's open source hardware, which is a slightly different term to open source software, but it means that all the stuff, like the circuit board design, it's all printed, so there are no surprises. And that's actually really, really important, because if you want to make sure that the voltage coming out of your device is within a certain threshold, well, you can go and check what the outputs are on all of these device characteristics. So that's just really, really, really good. It's a custom board. You can get other types. There's a different company called GHI Electronics, which make a lot of very, very similar devices. They're called Fez, freaking easy, which is wonderful. And you can take their open source designs and customize it yourself. Maybe you want to change the color of it or add some additional stuff on. You can do that. It's all open source. If you are worried by soldering, which I increasingly am, because every time I try and solder, I burn myself, there is something called a gadgeteer, which was really popular about a year or so ago. And it's more like Lego, rather than soldering in wires and stuff. It's a particular specification of device which come with peripherals which have well-known connectors, so you can just connect them in, and it tends to ship with loads of source code, so you can just get going in no time. So if you want an easier way in, and you don't have a soldering iron, and you don't want to burn yourself, then you can go with this gadgeteer product. Yeah, it's a product. There's also a Netduino Go, which is the same idea, made by the Netduino guys. Gadgeteer is by the GHI Electronics. So what would you do? That's a very quick sort of side step. If you have this amazing product that you've made on Netduino, and you want to ship it, well, it's as easy as going build, publish, and it outputs a particular type of file that then you ship up to your hardware manufacturer. And what they will do is when they're pressing out your hardware, they put the software on there automatically for you. So you wouldn't be able to plug in a USB cable to everyone's shoe. That would just be insane. But it may be fun before you get arrested. What you do is you ship it off this file format, which is effectively hard-coded version of your software that then they put in during the manufacturing process that then gets distributed. So, you know, if you talk about adverts for the cloud, if you don't actually have all of your logic on the chip and you actually have it in the cloud instead, you can actually have an upgrade path to something which typically you don't have an upgrade path for. So let's go and do some coding. Well, let's look at some pictures of code to start with, because pictures of code don't go wrong, and actual code does. So I'm going to do pictures to start with. So a primer on GPIO, General Purpose Input-Output, which is a pretty core part of the .NET framework, MicroFramework. And what it is a way of interacting with external devices. So maybe you have a buzzer or a screen that you want to update. Well, what you tend to do with simple things like the buzzer is you use an output port and send a message, maybe a binary message to say sound or stop sounding. So literally a 1 or a 0 down a cable, that's physically what happens. But in order to do it with C#, it's as simple as creating an output port. So the class output port is provided in the .NET framework in the namespace Microsoft.spot.hardware, which you can see at the top is included. You create an instance of this port and you pass it something called a pin. And you see here I have it pins.onboardLED. And that's an enumeration given by the guys at Secret Labs, who are the Netduino guys, to say what every pin, literally every part of those blue strips, and every connection onto the core CPU, this is what it is in which position, so how to address them. So you use this pins class. And that is effectively just an address. It's just an integer. And it means that the processor send a message down this particular channel. And then if you're doing something here, like creating, this example is flashing an LED, you want to send it a binary signal, a 1 or a 0. You do that by doing output port instance, in this case called LED flasher, .write, and then passing it a Boolean value, true or false. And it's absolutely as simple as passing it this true or false value, and it will send a pulse down the wire, which will then do whatever the output device is intended to do. And on the flip side of general purpose I/O, you can use the same style of code, sorry I have to go backwards here, to do inputs as well as outputs. So that's why it's general purpose input-output, because the same devices, the same pins can be configured rather than just being an output port as an analog input port, which allows you to do a read, as you see here, which returns an integer value, and that value simply says that whatever the current level is on that pin at that point in time, between 1 and 0 in this case, because it's a binary, it comes down as a number. There's another overload to this analog input called read double, which will give you a more granular reading. And we're going to be using this later to do a lot of our demos. So I'll skip ahead to cryptography. Right, so this has like been the bane of my life for the last couple of weeks, trying to get some of these demos to work, because this is what happens. If you try and use any of it, you get a not supported exception, which is because on the Netduino, they don't ship the crypto libraries. And the reason for that is there's not enough memory to do that and still have a large program. You can actually get them to work on here. You can compile your own version of the firmware and put it on top. It's all open source, and there's loads of guides online by the Netduino guys about how to do exactly that. So it's not even difficult. But the problem is, and the reason they don't do it, is that when you do that, you end up cutting down something called code space. And that's the amount of memory reserved for your code to run in and sit in. And that's not sort of putting objects in memory and manipulating. That sits in main memory, which is sort of aside. Code space is literally the amount of space for your binaries of your application. So if you put in the crypto libraries, you reduce by 20K the amount of code that can be in your code. And actually it means that you can only do up to 30K of your own code. And that's a problem, because even the simplest versions of this .NET MicroFramework programs, even just using something like an input port, will include assemblies as assembly references from Microsoft.spot and Microsoft.spot.hardware, and the simplest applications will end up being around 50 kilobytes. So that's a real problem if you only have 30 kilobytes. You end up having to do lots of workarounds for stuff, like not including loads of applications. So what do you do if, for example, you're trying to communicate with the cloud? The cloud uses a SHA-512 hash to authenticate requests going up. Well, it's C# or VB if you're a lunatic. You can just write your own implementation of the SHA algorithm, which it sounds a bit like a nightmare. Luckily, there are actually implementations out there that you can just take off the shelf and plug straight in. So I use this one from Elastacloudmp4, who's a Norwegian chap. maybe not chap, I don't know. Anyway, it's a very simple application. It doesn't use anything outside of system. It's got Microsoft Spot as a include as well, but as you see, it's not using because it's in grey. And it's a SHA-256 hash. Sorry, it wasn't 512, which is all you need for most of the Azure applications I'll be showing you in a few minutes. And then lastly, we're trying to communicate to the cloud. As we found out on our cloud day, where we didn't have any network access, it's very hard if you can't do network access to communicate with the cloud. So we need to have NetIO, which is network input-output sockets and all that kind of jazz. And quite unsurprisingly, it's really simple. It is using the system.net.http web requests. You know, the thing which is built into the standard .NET framework. You can use it in pretty much exactly the same way. So if you have code that currently works in a console app, you can literally just drag it into an application for the .NET MicroFramework, and it will just work, providing you don't do anything too elaborate, like try and connect over SSL. Of course, SSL requires crypto libraries, and the crypto libraries aren't involved on this chip. So if you've got to do SSL, you can still do it. The only problem you'll have is you won't be able to use this particular device. You can just get a slightly more capable device. In fact, the new Netduino Plus 2 has enough code space to be able to have the crypto libraries in. So when you come to look at this, if you try and buy one on Amazon, which is where you can get these Netduinos from, you simply probably won't have any of the problems that I've had. So, okay, so what does this do? It makes a request to Twitter, Twitter's API, using a HTTP web request. And then it does a stream read. And as you can see, it's got a stream reader. So simple C# constructs. It's got using statements, you know, for iDisposables. And it's, well, as you can see, it's very straightforward. Now, the sort of problem we often get, and the reason why the .NET MicroFramework it actually makes you a better programmer, is that if you try and read from Twitter, for example here, 100 tweets rather than one tweet like the previous slide did, you'll simply use all your memory up because you've only got 30 or 40 Ks worth of memory that you can access at runtime. So if you try and download, say, an image from something or 100 tweets from Twitter, and the size of that body in the HTTP web request, web response, is, say, 50 kilobytes or a megabyte or something, you try and read it all into memory by doing streamreader.read2end. It will use all your memory up, and then it will all fall over, and there you go. You can't do anything else. So what you have to do is use a buffering approach, and it teaches you, if you do this, that actually not being lazy about just reading everything to memory because I've got loads of it, and it teaches you to code in a very defensive way, and in a way which means that you're very light on actually memory usage. So you can see here, what we're doing is we're reading into a character buffer of a length of, I think it's 1024 bytes at a time, so a kilobyte at a time. And then we write the response out in debug.print, which is the same as the other one was doing, but the other one was, well, back a slide, please. The other one was doing read to end, and then writing all that in one go. So rather than going on the go, it's actually going a little bit at a time like that, and clearing down the memory every time it's done it. So you're not using all your memory up. Okay, so there's sort of core techniques. You have to do cryptography yourself, but if you've got input ports and output ports, and you have network access done for you very simply. So I'm going to jump into a demonstration. And this is a demonstration about reducing or removing the constraint on resource for storage. And the way we're going to do that is using the Netduino and its network connection to take data from a sensor, batch it, and send it up to Windows Azure table storage and Windows Azure blob storage at the same time. And what it has to do in order to do that is use network input-output. It has to do cryptography, which is the library, the SHA-256, that we've implemented ourselves. You have to do an interrupt port. We're going to do an interrupt port so that when I click a button, it's going to send the log file up, and normally it's going to send up sort of a row at a time to a table. And the reason we're doing this is that we want to turbocharge the device. Literally, this has got hardly any storage. You want to make it limitless by using the cloud. And exactly like I said, you can get 2 gigabytes on this SD card, which is actually quite unusual. You wouldn't necessarily put an SD card on one of these things. They're quite expensive compared to the price of the chip. But you could go from the megabytes of normal storage available to you on this to hundreds of terabytes, as we heard this morning, and more. And so I'm just going to drop into Visual Studio, and if we all just quietly say a prayer to the demo gods, it's hopefully going to be okay. Right. Okay, so also make sure I go on the right side of the screen. Okay. Cool. Now I can't see. Oh dear. Okay, maybe I come over here. Duplicate my desktop settings. Oh, okay, I'll just come over here, it's fine. I can use this, right? Yeah, there we go. Strangely, using my stomach as a mouse pad. Okay, interesting. Right, so, where are we? We are in program. Okay, cool. So, the thing about a MicroFramework, hello? Oh, that's a really good point. Got 10 minutes. Okay, it's going to be quick. It's going to be quick. Cool. Right. I won't drill into the detail, but first thing we have to do, rather strangely, is set the local time. These devices have clocks, but when you unplug them from a power supply, they don't have any onboard capacitance, so they will forget the time. If you're doing anything that needs the time as part of a request that goes up, for example, the XMS time headers for table storage, it has to be within 15 minutes of the correct time on the server. So if you don't have that, if it still says it's the 1st of January 1900, it will reject all of your requests. What we want to do is create a blob client and a table client. This is all our custom code, by the way, although it looks a little bit like the old version of table storage SDK that was recently replaced. It is our own custom implementation using HTTP web requests. What we do is we're going to create a table if it's not there, and if it is there, it will throw an error, which is a conflict, but we'll just sort of ignore that because it doesn't actually break the runtime flow. Then what we'll do is we will loop, effectively. So we will loop here in this while loop. And the while loop will read an input, which I've got from a potentiometer, which is a rotary encoder on a resistor. It gives you a value between 1 and 0. And it will multiply it by 40 to give us a faked out value between 0 and 40, which we can infer being a temperature. Then we're going to add that entity into table storage. And we're going to add it into a log file. You can see we're using a lock on a log file. So I did this basically just to show you that you can do locking. It simply is runtime thread coercion, the same way as you would expect to see it in standard C#, which is a monitor class for you VB heads. And as you can see again, file I/O done using file streams, file.open, file.write, that sort of stuff. It's all very standard stuff, but on a device. And we have an onboard button interrupt. So when I hit a button, it's already been adding row after row after row to table storage. But when I hit a button, it will find all those rows that I've also put into a CSV file, and it will transfer that all up in one go. Okay, so let's just run it. And I'll show you some of the wonderfulness of... okay, we've got a few breakpoints. Cool. F5 to run. Okay, if we go down to here, output. Okay, so you can see, again, sorry, I can't make this bit any bigger. Demo gods, demo gods. When this happens, what you do is turn it off and turn it on again. Okay, and then we'll F5 again. Does work, honest. So, 50 kilobytes. Not very much in this, to be honest, and it's, there you go, successfully assembly is successfully transferred. And now we're in a debugging context. So one of the first things it will do is pause before we hit here, because it's going over the network to get a network time in order that it can set itself up. Hopefully this bit won't work. This will work. Will work. So, how you doing? Ah, dear. Aha! No exception. Just a bit of a slow network there, so sorry about that. And you see it's got a network time back of the correct time, the 8th of the 11th in American format. And then we'll just step through quickly because I'm a bit short on time. We get a MAC address from the device so we can uniquely identify ourselves. We set a few things up. Create a table on Windows Azure table. Now, you see here, there was a resource was created because we printed that out inside one of the libraries. So if I go into Windows Azure management portal, which I'll show you in a second. No, actually, no, I won't. I'll show you in here. Our fantastic sponsors, Cerebrata, again, getting a bit of a mention. So if I go into tables, can't see what I'm doing. It's not their fault. There you go. So I've got a NatMF table. I just created that. And if I go back to Visual Studio, okay, we are going to set up a few more things. Okay, here we go. And it's going to output all the file names that are on the disk, but it's not really that interesting. Now we're getting quite interesting. We're going to get a value from our input port, which is this potentiometer over here, multiply it by a value, and that's our mock value of data. And then we're going to add an entity into table storage. So we do that, and hopefully we get into the line here. So we've got a line printed out over here, which says the resource was created. So if we go over here, again, we can see, let's see what I'm doing again. We should refresh the data in there. There you go. I have a new item added in. Now if I just go back to Visual Studio and run it a few times, we can refresh it and see that what we're doing. Oh, so let's run it once. Oops. That's done another one. I just changed the value of this potentiometer. And run it again. And run it again. And we'll go back to the lovely Cerebrata. And we'll refresh this. And you see the whole load of stuff with some different values on the temperature because we changed the value by turning the potentiometer. So that's proof of me not faking it, if little less. So I will hit the one last thing I'll do. I'll remove that breakpoint from in here. So it runs on its own, and I'll hit the input here, which is a button on the device to do an interrupt, and I will add a blob value. If a success, then say I've uploaded stuff, and if again we go back to Cerebrata, we can go into a blob container. Oh, there we go. Using the wall. This is all very high tech. Yeah, blob container. And we can see a demo container that I created. And we see we have got a bunch of stuff, which is now. And if that's really the time, I've got to carry on going. Okay, right. So I will skip demo 2 and just talk to you about the context of it. Okay, so demo 2 is about communicating between devices without having a connection. So a disconnected remote command. And the pattern we're using for that is to use a queuing mechanism in between the devices. So the devices can write to and read from queues. And because we're writing to a queue, nothing has to actually be there to pick it up. So that means we could have an on and off pattern for our cloud services. And also on the return side, we could have devices which only periodically look for commands and don't actually have to maintain an active connection to the internet at all points in time. The service bus is a natural way of doing this because it's very scalable. It means we'll be able to support lots and lots of concurrent devices. You think I've got time to do demo 3? Very, very quickly. Okay. Okay, so demo 3 is about using this lovely potentiometer that we have over here to spin up and spin down instances in Windows Azure. So, how easy is it to spin things up and down? Well, easier twiddling a little knob over here. What we're doing, because we don't have the crypto libraries, we're using a gateway architecture where we have a service already in the cloud which understands all the crypto things that it needs to in order to communicate with the Service Management API. And the idea is that our device sends a message up to the gateway already running on Windows Azure, and that gateway communicates with the Windows Azure Fabric to change the number of instances in a role which is already running. As you can see, because there is no SSL, we have to use the gateway approach. But if you had a larger chip, you could do this natively on board. So, let's go to, actually, I'll just do this. Simple scaler over here. Okay, so it's the world's simplest demo, luckily, for everyone involved. And what it does is we create our analog input, again, same as always, to allow it to communicate with its I/O, so it can see what the number of instances that it should have. And we read the value of the potentiometer, multiply it by 10, so the maximum we ever get is 10, the minimum we ever get is 1. And it checks the current state of what's happening in Azure, and it sends a message off in order to change the number of instances from whatever it was to the value that you've done with your potentiometer. In the cloud, it will then take that message, build a service management request up, and will then go on and make a scaling request to Windows Azure. So, without further ado, and it's very simple in that it's just using HTTP web requests in order to do this stuff. And to the wall. What are we doing? This one is very, very simple, a lot smaller than the other application demo that I showed you. So it's only 42 kilobytes rather than 54, whatever the one was. Right. So, okay. We're going to, as always, step through. Really slow network here, which isn't helping.
Because you're going to a gateway, you're not having to sync your time.
No, exactly. Yeah. Good spot. Yeah. The time syncing is literally if you're communicating directly with the services that you need to agree with. What's happening on the gateway is that it's got a time which is pretty much accurate, and it's using that. Okay, cool. So we have the current state, which hopefully will be like unknown, because we haven't made a request yet. And what we're going to do is read that value, and that value is, what's that? 6 point something. So we're casting it to an int to drop off precision. Not a very nice way of doing it, but it works. And then it's going to literally jump through there. And if I can go to the Service Management API, we can see that an update is in progress already. So if we, actually it might be old. It should hopefully say upgrade and it's going to 6 with a bit of luck. And then I shall finish off my presentation. Sorry for running over. Very pretty, I really love this portal. It's beautiful, but I've just seen it do that too many times, unfortunately. But there you go, 6 instances, and there you go, already done. It's very quick to reduce the number, it just doesn't drop them off. But there you go, 6, powered by Netduino and a little dial.